Welcome to PFT Tutor with Jeffrey Haynes. In this video, we're going to discuss a troubleshooting event triggered by an alveolar volume value greater than the total lung capacity, which is physiologically impossible. Most of you probably do not use the DLCO system used in this case, but I hope you'll still find it useful for me to explain my mindset and approach to troubleshooting. One of our superb technologists was performing a test and recognized that the patient's alveolar volume from DLCO was significantly higher than the patient's total lung capacity. As I mentioned, this is physiologically impossible. But what is not obvious is which parameter is inaccurate. Is the TLC falsely low or is the VA falsely high? To help determine which value is in error, the technologist performed a test on herself, and her total lung capacity was compatible with previous tests with a z-score of 0 or 100% of predicted, but her VA, her alveolar volume from the DLCO, was significantly higher than usual with a z-score of 1.85 above the upper limit of normal. So it appears that a falsely elevated alveolar volume, or VA, is the problem. And if you have a falsely elevated VA, that's also going to create a falsely elevated DLCO, because DLCO is the product of the KCO, or transfer coefficient, and the alveolar volume. So if we multiply the KCO of 3.76 times the alveolar volume of 6.43, we'll get a DLCO of 24.17. However, if we substitute the technologist's TLC for the elevated VA, we'll get a different outcome. So if we multiply the KCO times 5.69, her TLC, then we will get a DLCO of 21.39. The next thing we did was run a DLCO simulation with a 3-liter syringe. This is our Levy-Jennings plot. So this is the average value for our weekly measurements. The dashed lines represent 3 standard deviations. And you can see that this is much tighter than the ERS ATS ranges. And in previous videos, I encouraged people to create their own limits based on the performance of their machine using 2 or 3 standard deviations. The measured VA in this case, as you can see, is much higher than both thresholds. After completing the DLCO simulation, I ran a DLCO BioQC test on myself. So this is my average value here in the straight line. These 2 closest dashed lines represent 2 standard deviations, and the outside dashed line represent 3 standard deviations. And you can see that my alveolar volume is much higher than we usually get doing BioQC testing. So now we need to do some troubleshooting and figure out why is the alveolar volume reading so high. I don't like to throw darts at a dartboard, just doing random things and hoping it works out. I use a very standardized and I think logical approach. I'm going to share that with you now. So to figure out why the alveolar volume is reading high, it seems logical to think about how the alveolar volume is calculated. So the alveolar volume is the inspired volume minus the dead space multiplied by the concentration of the tracer gas the patient inhales, in this case helium, divided by the concentration of the tracer gas in the alveolar sample. So let's think about the inspired volume and the dead space. Well, the dead space would be an unlikely cause of this unless someone were to put extra tubing on the system, or if someone went in and made a change in the settings. That's not likely to happen in this case. But maybe the inspired volume is inaccurate, so that would certainly cause a problem. And so the next thing we did was we checked the flow calibration on the system, and as you can see, all the values are right in control. There's no evidence here that there was an inaccurate inspired volume causing the problem. Let's move on to the other side of the equation and look at the measurement of the tracer gases. So if you had a leak in the system and the helium was leaking out of the system, this could cause an abnormally high alveolar volume. So what we did here was we did a mouth pressure calibration. And on this system, the mouth pressure calibration is recommended every 3 or 6 months, something like that. We do it every single day. And the reason why we do that is because we're not really calibrating the mouth pressure. We're checking the system for a system leak. A piece of tubing is disconnected or something's not tight. So we did this, and there was no evidence that there was any kind of major leak in the system. Another potential cause of an elevated alveolar volume is an inaccuracy in the helium analyzer. So in this system, the helium analyzer is calibrated with a gas sample that's put into the inspiratory bag. And so we ran a gas analysis, and as you can see here, the helium is depicted in the blue line, and that reaches its target, so there's no problem with the helium analyzer. So I mentioned that this system uses collection bags. So this large bag here is the bag that the patient inspires from, that has the diffusion test gas in. And it's hard to see here, but I put an arrow. So once the patient exhales and the washout volume is diverted out into the room, this bag here collects the alveolar sample. And if there was a problem in this bag, you could have an elevated alveolar volume. And this bag is not tested when you do the gas analysis, and it may escape detection with doing the mouth pressure cal. So we went ahead and changed that small bag that contains the alveolar sample, and then we repeated the DLCO simulation, and the VA is now back within the normal range. Then we repeated the BioQC testing on myself, and my alveolar volume went back into the normal range as well. So I tried to find a hole in the bag, and I couldn't visually see one, so I hooked it up to a 3-liter syringe and put some pressure into it, and hoping that that would show me where the leak was, but I couldn't see a leak even with adding pressure to the bag. And it's not terribly surprising that I couldn't find the leak, because it's only going to take a small hole for helium to leak out, and this is dictated by Graham's law of diffusion, where the rate that a gas will flow through a small orifice is indirectly proportional to the square root of its molecular mass. So helium, having a low molecular mass, can leak easily out of a small hole. But I don't give up easily, so the next thing I did was I filled the bag with water, and the red arrow shows the leak, and it was leaking right where the plastic bag met the plastic connector. We keep a corrective action log for all of our machines, so we can use this for future reference by the technologist if a similar problem arises and how it was fixed, and it can be useful too for technical support. Key points: the alveolar volume should never be higher than the total lung capacity. That's physiologically impossible. Weekly DLCO simulations and BioQC testing provides historical data to help determine if a problem exists, and if so, what's the nature of the problem. Understanding how questionable values are measured and calculated will make the troubleshooting process much easier, and always document troubleshooting events for future reference. Thank you for watching PFT Tutor with Jeffrey Haynes. Please click the like, subscribe, and notification buttons, and we'll see you next time.